Hello everybody, my name is Guilherme Eymael, and in the summer of 2021 I worked on the MIT Department of Aeronautics and Astronautics through the MIT Summer Research Program on a project called Deep Artificial Neural Network Model for Improved Thermospheric Density Prediction. And to give you a little bit of background of why this project is needed, as you can see in the chart, there is an increasing number of satellites and debris, and because of that, we need a more efficient space traffic management. And in order to do that, it's critical for us to better determine and predict satellites' orbits, so we can avoid collisions between satellites and debris and the cascade effect that comes with that. Um, so satellites' orbit inaccuracy is actually due to uncertainties in drag force calculation, and usually the biggest error comes from the thermospheric density term. And we are specifically concerned with the thermospheric density because, as you can see in the chart on the left, that's the uppermost layer of the atmosphere, and that's where most of the low Earth orbit satellites reside. And right now, there are two estimation methods for thermospheric density. The first one is an empirical model that uses data collected from satellites. And even though it is computationally fast, it gives us not the most accurate model, and it lacks also predictability capabilities. Um, when the physics-based model is actually the most accurate one with good predictability capabilities, but it's very computationally expensive because it needs parallel computational resources to solve the 3D Navier-Stokes equations and continuity equations for the high fidelity model. So our objective with this project is to train a deep learning model for thermospheric mass density prediction with the computational speed of the empirical model and the predictability capability of physics-based models. Um, in order to do that, we use proper orthogonal decomposition as our verification method for the reduced order model. The POD is a mathematical model that computes the linear subspace of the data structure, and we use dynamic mode decomposition with control for data propagation into the future. So we basically have the reduced order model states now, and then we have the space weather input that predicts how the density is going to evolve with time. And in the left, you can see the true density, the predicted density, and the absolute percentage error for a propagation of 24 hours. Our second reduced order model, or the one that we are most interested in, is a machine learning where we replace the POD for a variational autoencoder, which we can now find the nonlinearities of the systems, and we have a dimensionality reduction from 10 to the fourth to 60. We also use dynamic mode decomposition with control for time propagation, and for training we use population-based training, in which multiple networks with random hyperparameters are simultaneously evaluated and refined to find the best network. So here are some of the results. In the left, you see that our machine learning reduced order model performs with a similar accuracy as the proper orthogonal decomposition reduced order model. And the peaks in the absolute percentage error correspond to the increased solar and geomagnetic activity from the plot in the left. And the absolute percentage error increases with time due to error propagation. So our next steps are going to be to better train our machine learning model, try to come up with different more efficient architectures, and use a recurrent neural network instead of dynamic mode decomposition with control for time propagation. I hope you liked to hear about my research, and if you have any questions, I'll be happy to answer.